So in order to develop an understanding of a radical approach to embodied cognitive science, an approach that's not computational, that's not representational, right? Um, it can be helpful to consider a few points. And here I'm giving you a description that's provided by Larry Shapiro, um, on, commenting on Andy Clark's work, right? Um, and so Clark identifies six um, principles or features that help us understand embodied cognition. And I'm going to go over these. So the first is non-trivial causal spread. So to understand this, consider how in good old-fashioned artificial intelligence and traditional robotics, there was no causal spread. Here's what I mean by that. So behavior is caused entirely by processes that are local and internal. Think again about localism, smallism, right? In these classical systems, behavior is caused by something internal, right? So that robot there that's failing to go upstairs, um, the way it's operating is through active control, internal control of every joint angle at all times, right? So the the behavior is caused by something internal. It's not distributed. It's not spread. Um, so embodied cognition involves then causal spread in a non-trivial way, right? And the idea is that bodily and environmental structure can enable agents to do things without needing complex internal processing and planning. The slinky going downstairs provides a good example, right? So going downstairs, it's not controlling. There's no internal controller, managing the uh, any change in the slinky, right? It's just the structure that the slinky has and interaction with the environment, right? Um, it makes it possible for the thing to just go downstairs without controlling what it's doing. Um, the passive dynamic walker is a good example of something similar to, right? So this is one illustration of this kind of dynamic walker. This is research coming from Japan. Um, and you can see that the the walker there is on a treadmill and it's walking, right? It's moving forward, and the the researcher there is, just trying to make sure it doesn't fall down or anything. But if you let it, it will keep doing this thing, and there's no controller there. This is not a there's no electrical or electronic component here. There's no control of joint angles. It's just a mechanical structure, right? And the mechanics of this body are such that it enables when the environment uh, does its part, right? So the surface that the walker is walking on is moving, right? Um, then then the body parts will make it possible for it to move forward. And this case is, as you're saying, but they can exhibit the same kind of behavior if you put the walker in an inclined slope, right? If it's going downward, um, if the incline is downward, then the walker will actually go down on its own, just because it's the structure of the body and of the environment make that behavior possible. So there's no internal causation of the behavior. The behavior is the causation is spread to the body and environment. A second important feature of embodied cognition is the principle of ecological assembly. So the idea is that solutions to problems are soft assembled from neural, bodily, and environmental resources as needed. So the key concept for us here is the concept of soft assembly. And to understand it, we contrast it with the concept of hard assembly. Right? This is when a set of parts play a specific, predetermined, and unchanging role that completely defines the behavior over time. So this is the case for any machine that you have, right? Your computer, um, any kind of a calculator or whatever it is, your iPod. Um, the machines that we design and build, they are hard, they exhibit hard assembly, right? Because the parts play a very specific role that's predetermined, and it doesn't change over time what each part does, right? You put a part there to do a specific thing, and that specific thing won't change over time, the specific thing that the part does. In a soft assembled system, in a system that exhibits soft assembly, then these features are different. And that's what we see in swarms, flocks, and schools of fish. Um, there's um, a dynamic coupling of the parts, and the behavior of the parts can change over time. The system um, the behavior of the system will change over time with changes in the role that each part plays. And so the idea then is that solutions to problems, uh, cognitive performance, results from the soft assembly of interacting parts, right? Interacting parts that change their role over time, and these are coming from neural, bodily, and environmental resources. So the dynamic coupling forms a temporary system, and that's what we do, for example, when we use a map for navigation, when we use pen or paper to take notes or to do mathematics, when we rely on our phone for storing contacts. We're forming a temporary system that brings together parts that are neural, bodily, environmental, or material, and temporarily a system is assembled that performs the task, that solves the task. But this is, again, soft assembled. It's not a question of hard assembly, because it's not a unchanging system. It's not a fixed, rigid system, right? The system, the role that the different parts play over time can change, and it's a temporary system. It will go away as soon as you arrive somewhere. You don't need the GPS anymore, or the map, right? And so you then reorganize your activity to do something else. You reorganize your bodily structure, and you couple to other objects to perform other activities. The third feature is can be referred to as open channel perception. And this is the idea that perceptual systems are constantly connected to the world, and they rely on this constant connection to the world to simplify tasks and reduce the amount of information storage that's required. A traditional example of this is the outfielder problem in baseball. Right? The outfielder is this player there that's positioned in the outfield and is waiting for the ball to come, and the objective there is to catch the ball in the air. If the ball touches the ground, then that, given the rules of baseball, that will count differently. So the key thing is for the outfielder to catch the ball, the fly ball, as they say, catch the ball in the air before it reaches the ground. So how does the outfielder do that? Right? What's required for catching the ball successfully in the air? One approach to explain this would be to say that there's a lot of calculation, internal calculation involved, and so the player needs to compute the ball's initial conditions, predict a trajectory, and estimate some possible landing point, and run there, right, and then update the model on the go as the ball continues flying and the player is getting toward the predicted place. You update the model and generate a new prediction, right? And so on. So there's a lot of internal calculating there, a lot of mental gymnastics. With open channel perception, you don't need to internalize all of that, because the world is available to you and it's changing right in front of you. So you need to change you don't need to change an internal model of the world if the world is changing right in front of you. You rely on those changes, right? The world is updating itself, so you don't need to update an internal model of the world. So this is what some people refer to as online control. So one possible explanation for how to catch the ball is to know optical acceleration and changing bearing direction. So if the ball is increasing in size, right, uniformly at the center of your field of view, that means that it's coming right directly toward your face, right? If the if the ball changes in direction in this way or that way, then it tells you that it's not going toward you, right? So all you need to do is know this kind of displacement in your visual field, right? It should be coming directly toward you like this. And then radial and lateral movements are independent. You just move your body so as to um, um, do away with the change in how the ball is relating to you, right? This is one hypothesis for how to do that online, right? So the position of the ball is changing right in front of you. You don't need to calculate it. You just change your position in relation to the ball so that to your position to catch it. So open channel perception. If you have open channel perception, you don't need to internalize and calculate things inside. Another feature is information self-structuring. The idea is that perceiving and acting are inseparable. And typically, perceiving involves acting to make more and better information available. Right? Perceiving requires acting. Perceiving is active, right? And you act to perceive more and better, and you perceive to be able to act better in the environment. Right? There's this kind of entailment of perception and action, and this reciprocity of perception and action. One example of how information becomes self-structured here is what I've described before, the example of optic flow, right? So when you act in a certain way in the environment, when you move forwards or you move backward, then that will change the information available to you. And it will change in a way that's specific to the movement you performed. If you go forward, it will change in a way that's specific to moving forward. If you go backward, the change will be specific to moving backward. Right? And so there's this kind of reciprocity. The information becomes structured by your action. Right? And so the information available for perception becomes structured by the way you're acting in the world. So again, optic flow is an example of this, but this relates also to the importance of morphological design and action, right? So eye and head movements would give us an example of this. But if you think of pigeons, for example, how they bob their head for depth, right? They're constantly moving their head like this. And this is the sort of thing that enables them to perceive depth. Right? We are actually moving our bodies in more ways than we might be aware of. Right? One thing that we can do is move our eyes a lot too, right? And there are micro movements, saccades and things like that, right? So our eyes are constantly moving, and this is a way in which even if your body is still, you're sitting somewhere, you're not moving in any way that you can perceive, your eye is moving, right? And that is sampling the environment, not to internalize information, but to attune to what is out there, to information, and actually to generate structure in the information, right? By doing these micro movements, you're generating structure that's informative of the environment and your relation to it. The fifth point is thinking of perception as sensory motor experience. So relates to the previous point. It is that perceiving and acting flow into one another. Perceiving leads to acting. Acting leads to perceiving. Right? But the point here is that this forms a sensory motor loop. And this loop partly includes the environment itself. Right? So the locus of experience, the location of experience is not in the brain. Right? You don't have experience in the brain. It's not a Cartesian theater. Right? So instead, there are cycles of organism-world interactions. There are these loops of acting, perceiving, right? Loops that involve the brain and the body and the environment in constant interaction. The last point in this list provided by Clark and described by Shapiro is described as dynamical computational complementarity. And this is the point that we'll take issue with, right? Everything I've described up until now are points that a radical approach in embodied cognition, radical approach to embodied cognitive science takes for granted. But this sixth and final point is where we will disagree with Andy Clark, right? So Andy Clark in this 1997 book describes radical embodied cognition. He actually came up with the term, with the name, radical embodied cognition, and then people like Tony Chimero embraced it and said, yes, that's exactly what we're doing. We're doing radical embodied cognitive science, right? But so Clark is describing radical embodied cognitive science here, and he says, this is the thesis of radical embodiment. The thesis is that structured, symbolic, representational, and computational views of cognition are mistaken. In this thesis, right, is that embodied cognition is best studied by means of non-computational and non-representational ideas and explanatory schemes involving, for example, the tools of dynamical systems theory, the conceptual and mathematical tools of dynamical systems theory. Right? But Clark says the thesis of radical embodied cognition is thus, it seems, a genuinely held view. Some people do adopt it. And he says it involves a rejection of explanations that invoke internal representations, a rejection of computational explanation in psychology, and a suggestion that we would be better off abandoning these old tools in favor of the shiny new implements of dynamical systems theory. But Clark says further, such radicalism, I believe, is both unwarranted and somewhat counterproductive. It invites competition where progress demands cooperation. So Clark is saying, no, we don't need to choose between dynamical explanation and approaches or computational explanation and approaches. Why not do both, right? That's why he says there's a complementarity between them. And while it's true that it's possible to combine these approaches, those of us working in radical embodied cognitive science actually think that that's not the best use of the tools. So again, if you think of this quote by Gibson, he says, the rules that govern behavior are not like laws enforced by an authority or decisions made by a commander. Behavior is regular without being regulated, right? So there are regularities in behavior, and we try to understand those regularities, but not in terms of internal rules, right? The behavior is regular, but it's not regulated. And so the goal then is to study those regularities as ecological patterns of change over time, right? Patterns of change over time in the organism-environment relations. So we understand them in terms of perception-action coupling. And there is a very fundamental disagreement there on what the system in question is, right? What's the nature of the cognitive system? And that's a reason why we think it's not the best way to think of dynamical and computational approaches as being complementary, right? As if you can combine them. It might be possible to combine them, but deep down, the assumptions are incompatible, right? So Tim Van Gelder, one of the developments and proponents of the dynamicist approach to cognition, he says this about the nature of cognitive systems. He says the claim that cognitive systems are computers and the competing claim that natural cognitive systems are dynamical systems. Each of these claims forms the technical core of a highly distinctive vision of the nature of cognitive systems. They give rise to highly distinctive ways of understanding cognitive systems. So describing the computational approach, Van Gelder says this, note that because the cognitive system traffics only in symbolic representations, the body and the physical environment can be dropped from consideration. It is possible to study the cognitive system as an autonomous, bodiless, and worldless system whose function is to transform input representations into output representations. Right? The body can be completely ignored. The dynamicist approach relies on a completely different understanding of what cognitive systems are and how they work. Right? So he says, as we have seen, dynamical systems are complexes of parts or aspects which are all evolving in a continuous, simultaneous, and mutually determining fashion. It's not independent parts doing their own thing, but it's parts who interact with each other and who can change what the other is doing, and they change what they are themselves doing. So he says if cognitive systems are dynamical systems, then they must likewise be complexes of interacting change. Since the nervous system, body, and environment are all continuously evolving and simultaneously influencing one another, the cognitive system cannot be simply the encapsulated brain. Rather, it is a single unified system embracing all three, embracing brain, body, and world. Right? So you might be able to use mathematical models of dynamical systems, and also use computational modeling. But the point is that there is benefit to considering deep down the assumptions that go into using one approach or the other. Right? You're conceptualizing the cognitive system very, very differently. And the system itself, the cognitive system, is either one kind of system or the other kind of system, even though you may be able to model it in different ways, right? The system itself either is a dynamical, complex system, or not. Randall Beer is a researcher that develops this kind of dynamicist approach in cognition and robotics. And this image gives you a picture of how he sees the nervous system as being embodied and the body being situated in the environment, right? And they're interacting with each other. The brain interacts with the body interacts with the brain and with the environment, right? There's this mutual determining relation there. And he encapsulates this perspective in the following. He says, an embodied nervous system can utilize the natural biomechanics of its body, the geometry of its sensory surfaces, and its ability to actively control these surfaces to considerably simplify many problems, right? The embodied, if the nervous system is embodied, it can use these resources in its favor to simplify what otherwise might be very complicated internal, mental gymnastics. Likewise, a situated agent can utilize and manipulate the physical and functional organization of the space around it, as well as the social organization in which it exists, to offload problems to its environment. So if the agent is situated, then it can offload a lot of the burden, right? Cognitive burden, cognitive load into aspects of the environment, which includes the social environment. On this view then, cognitive behavior arises from the interaction between a brain, a body, and an environment, and cannot properly be studied as a product of the mind-brain alone. Right? So you see, it's a radically different assumption, right? And the computational paradigm will say that we do understand behavior in terms of the workings of the computational, the algorithm, the computational procedures, right? So there will be a level of mind, or similarly internalist explanations at the level of the brain, right? The level of implementation, neural implementation. Right? And that's very different from saying, no, we actually, we can describe what the brain is doing, and we should describe what the brain is doing, but that's not going to account for cognition. We can't properly understand cognitive behavior in terms of what the brain does. Right? We need to understand what the brain does in relation to what the body does and in relation to the characteristics of the environment. Right? We need to understand each of these components as components of a dynamical system, a complex system interacting with each other. Right? But the explanation won't be in terms of one part, because that will be a subsystem. Right? You need to understand the behavior in terms of the system as a whole. And Shapiro encapsulates the perspective saying, the body is the brain's partner in the production of cognition. The body incorporates passive dynamics, structures information, right? And it determines unique sensory signatures that help to create perceptual experience. The body and the brain divide the labor of cognition between them, sharing in processes that neither the body nor the brain could complete on its own. So the point then is that when you take the approach of reconceptualizing cognition in dynamic terms, right? When you adopt the naturalistic, functionalistic, constructivist approach to cognition, understanding in terms of relations, then you're going to be engaging in a dynamic way of thinking, which will require a dynamic reinterpretation of what the brain itself is doing as contributing to the system, but not performing the whole activity that the system performs. That's kind of an overview of key features of embodied cognition, and the contrast then between thinking, in computational terms and dynamical terms, and how the assumptions that go into thinking in computational terms or dynamical terms are incompatible, right? And so it is more fruitful to develop fully the computational approach and develop more fully the dynamical approach and see how far you can get with that approach by itself. It will involve dynamically reinterpreting the components of the system as components of a dynamical system, components that interact with each other and change the contribution that each makes to the behavior of the system.